In the last session, we have learned how to write a spice model for different circuits. So first we learned how to write a spice model for the simple network consisting of one DC source and two resistors R1 and R2. And we also have written down the 5 steps which are involved in writing a spice model, that is defining all components, active and passive. Second step is define all the sources, that is voltage and current, whether it is independent or dependent. Third is define the type of analysis to be performed, whether it is operating point analysis, DC analysis, AC analysis, transient and noise. Fourth is we have to include the model files. And fifth is we have to define the type of outputs you want to observe. So in this spice model for this simple circuit, we have learned how to write in the model to perform operating point analysis. So it is here. So if we use the directive.op, the spice engine understands that it has to perform an operating point analysis. So we also learned that how do we define a component. Basically we have to define a component in terms of the nodes between which it is connected and the value. So R1 was defined as R1 space 1 space 2 space 1k. R2 was defined as R2 space 2 space GND 2k. Similarly, the source Vin was defined as Vin space 1 space GND space 1. Okay, so this is how it was defined. So we have to always remember whether it is a simple circuit like seen here, or whether it is the spice model for plotting the IV characteristics of an NMOS or a PMOS, we have to follow these 5 steps. Okay, so always remember, define all active and passive components. By active we mean transistors, and passive we mean resistors, capacitors, inductors. Then you have to define all the sources in the circuit, define the type of analysis, include the model files, and define the type of outputs you want to observe. So we learned that what is the format to define a MOSFET. So this is very important because today we are going to write a spice model for plotting the VTC or voltage transfer characteristics of a CMOS inverter. So we have to always remember this format. So syntax for defining a MOSFET is the alphabet M followed by the device name. So you can give any device name here. So it is a concatenation between alphabet M and the device name. Then drain, gate, source, body, library link name, width and length values. So based on this format, what we did is that if you wanted to plot the IV characteristics of an NMOS, we have actually drawn a circuit involving the VGS source V1, VDS source V2 and all the current directions. We also had terminalized the circuit. So we indicated drain, gate, body and source terminals. We also short circuited body and source terminals. So VBS is equal to 0. Hence there is no body effect. And most important thing is that we have to define unique nodes in the circuit. So we have defined node 1 in the input side and node 2 at the output side, so that we can define the source V1, source V2, and also we can actually write the description of the MOSFET. That is why defining the unique nodes in the circuit is important. At the same time, defining the terminals of MOSFET is important. So depending upon to which node, which terminal of MOSFET is connected, we have written M. So N1 is the name given to the device, and the library link name is N_MOS. So we have written it as MN1, where M indicates that it is a MOSFET, N1 is a name. So MN1, and we can see here drain connected to node B, gate connected to node 1, body and source are connected together and they are connected to ground. So we have written MN1 space 2 space 1 space ground, library link name, and we have taken width and length as 4000 nanometers or 2000 nanometers. So there are different alphabets which are available. So capital T is for tera or 10 raised to 12, capital G is for giga 10 raised to 9. Then we have MEG meg, not capital M, because capital M is reserved for MOSFET description. So we do not use capital M for mega, we use meg. MEG means 10⁶. Then we have K, kilo, 10⁵. And then we have small m 10 power minus 3, we have u 10 power minus 6, we have small n which is 10 power minus 9, we have small p 10 power minus 12, and we have small f 10 power minus 15. So all powers spanning 10 raised to plus 12 to 10 raised to minus 15 are considered in the language. Then we have defined the DC sources V1 and V2. Then we have linked. So the syntax for defining the model files is the directive dot model space library link name space library name and level. And last is we are going to define what kind of output we want. That is, we have said dot print. So dot print is a directive which is meant for plotting the output. So always understand that dot print is common. Whether you want to do DC analysis, AC analysis or transient analysis, dot print is compulsory. So we have said, because we wanted to plot IDS versus VDS for different constant values of VGS. So what we have done is we have written dot print space capital I. So capital I alphabet indicates to the engine that we want to plot current. So dot print space capital I in parenthesis current through the device MN1 comma V2. Even if you write down just I parenthesis mn1, it is still okay. So dot print space capital I parenthesis mn1 indicates that you have to print or you have to plot the current flowing through mn1 and v2. And we have varied v1 and v2 here in the step number 3 dot dc. So v1, that is VGS, is varied from 0 to 5 in step of 1 volt, which will give us a family of curves. VGS is equal to K1, K2, K3. And similarly, we have also varied the VDS voltage, that is V2, from 0 to 10 in steps of 0.5. So we have 20 different values for V2 and 5 different values of V1. So ultimately, if we had a spice engine with us, which is not there, and if you would have run this program there, we would have got a family of curves, that is 5 curves for IDS versus VDS for VGS1, VGS2, VGS3, VGS4 and VGS5. Okay, so taking a discussion ahead, we are going to today learn many different directives, and also we will write the spice model for CMOS inverter. Okay, this is a brief revision of spice language we did last time. Now we go ahead. First agenda is write a spice model. Write a spice model to plot VTC, voltage transfer characteristics of a CMOS inverter. Okay, and second is we are going to speak about crosstalk. Yeah, so spice model for plotting VTC of CMOS inverter. Okay, see, now first we'll make the basic transistor level schematic of CMOS inverter, and then we'll convert it into a schematic which will help us to write a spice model. So first and foremost, what we do is we will draw the basic CMOS inverter. So this is how you draw for making the layout, right? So here say this is V in and this is V out. Okay, and we know that we have to apply a clock here. Okay, so now what we do, I will modify this transistor level schematic into a schematic which is suitable for writing a spice model directly. To see how I do it. So I will draw the basic transistors, but then I have to add certain things. Just when there is some bug here. Okay. Now instead of VDD, what I will do is I will show this VDD as another supply. You can even keep it as VDD, not an issue. So plus and minus, and we will say VDD here. Now I will make the basic connections here. Here, what I will do, I will show V in as V in, and this is a clock. Okay. Now what I do is I will terminalize the devices. So source, drain, drain, source, gate, and gate. Now what we will do, we will give names to the devices. Okay, we will do the naming. So the name of PMOS will be P1 and the name of NMOS will be N1. Okay, so we will give the names. Another important thing is that we are going to define nodes now. Okay, so let this node be node 1, let this node be node 2, and let this node be node 3. Okay, so 3 is the output node. We can actually show it like this. Okay, and we can say this is V out. Okay, so now one more thing which is important is we have to give library link name. So let P1 have the library link name P underscore MOS. Similarly, let the NMOS have the library link name N underscore MOS. Okay, let us give different color. So library link names, the device names, the nodes 1, 2, and 3, and all the terminals also. So I think so this is more than sufficient. Now understand one thing, that just like we define DC sources in SPICE model with the directive .dc, similarly there are different directives for defining a clock. So clock in the SPICE language is called as transient source. So now we are aware about how to define MOSFETs. We are aware about how to define normal DC sources, but we do not know how to define transient sources. So the first thing is to learn the syntax for defining a transient source. Once we learn the new things, then we can incorporate all the new things, and then we can write the SPICE model for plotting the VTC of a CMOS inverter. So syntax for defining a clock signal in SPICE. Okay, so understand one thing, that .tran. Okay, so instead of .dc, we use the directive .tran, and see it is having many parameters. Please see carefully. The first parameter is the initial value. There is no comma here. Space, final value space there is a delay. Do you want to delay the signal with respect to t equal to 0? Then we have rise time, then we have fall time, then we have on time, and then we have the time period. Okay, so how many parameters are there? 1, we have initial value, final value, delay, rise time, fall time, on time, and time period. We have to follow the syntax. Okay, so we will assume that my clock should go like this. It should be 0 volts and 5 volts. So initial value is 0 and final value is 5. There is no delay. So remember this thing, that all these parameters from here to here, all these parameters from here to here are defined in nanoseconds. Okay, so using the keyword nano. Okay, they are all in nanoseconds. Okay, so let us assume that my clock should have a frequency equal to 1 over 8 nanoseconds. Okay, so I think so 1 over 8 nanoseconds would be about 125 megahertz. Okay, no issues, we can also keep it 1 gigahertz. Okay, so we will assume that let frequency of input should be equal to 1 gigahertz. So T is equal to 1 upon Fn equal to 1 nanoseconds. Okay, so we want the clock to have a duty cycle of 50%. So if T is equal to 1 nanoseconds, naturally my T on will be 0.5 nanoseconds. Also note that one cycle of the clock, that is input, will take 1 nanoseconds. That means 5 cycles will take 5 nanoseconds. You will come to know why I am writing all these things. Okay, so now the way to define is like this. Now this is how we define a clock source, which is called as transient source. Now just like in our spice model for NMOS, where we wanted to plot the output characteristics or the output current versus VDS, here also we have to do different analysis. So for plotting the output characteristics, that is DC characteristics of an NMOS, we have used dot print DC and we have done a DC analysis, but here we have to do transient analysis. So dot tran, I'm very sorry, I have used the wrong word. It is not dot tran, it is pulse. Very sorry. So we are supposed to use the keyword pulse. Okay, so pulse is the keyword which is used for defining a clock signal in spice. Now how to define the analysis? Second new thing which we have to learn is to perform a transient analysis. So just like we say dot DC for doing DC analysis, the directive for performing transient analysis is like this. It is dot tran, and then the parameters to be passed are very simple. It is step time, or we can say time step. Okay, time step. Okay, so it is time step and time stop. So for how long you want to perform the simulation. So if suppose I want to perform the simulation for 5 cycles of the clock, I have to give 5 nanoseconds here. So I can write down here. Okay, I can write down here dot tran. I can say 0.0 nano space 5 nano. That means what? The step size is 0.01 nanoseconds, and I have to perform the simulation for 5 nanoseconds or 5 cycles. Similarly, here also we can write down pulse, initial value is 0, final value is 5. I do not want any delay, so I will say 0 nanoseconds. Let the rise time be 0.1 nano. Let the fall time also be 0.1 nano. And my on time as per the frequency of 1 gigahertz is 0.5 nano. And my time period is 1 nano. So basically we have to incorporate this statement as well as this statement in my spice model. Okay. Third important thing is that we have to tell what kind of output I want. Now I want to plot V out versus V in, which is called as VTC. Now please see here that in this particular schematic, the output voltage is available at node 3 and input voltage is applied at node 1. So node 1 is input voltage and node 3 is output voltage. So how we have to do this? It's very simple. We have to say dot print. Instead of dot print DC, I will say dot print transient, and I will say plot V bracket 3 space V bracket 1. Okay. So V bracket 3 indicates V out and V bracket 1 indicates V in. Okay. So I will make a comment here that 3 is my output node and 1 is my input node. So now 3 things which were new we have learned. Now we will add these 3 new things to the older things which you already know. So step number 1 is define all the active and passive components. So your active components are 2 MOSFETs. So see now what I will do. So we'll go back and forth. So now we will actually have the spice model. Okay. So complete spice model for CMOS inverter. If you want, then I'll bring that model here so we don't have to scroll again and again. Something has got cut, no problem, we will rebuild it. Okay. Yeah. See now, it's very easy now. So complete spice model for CMOS inverter. Okay. So we will define the PMOS first. So alphabet M, P1, MOSFET P1, drain, gate, source, body. So drain of P1 connected to node 3. So okay, if you want, we will write it. Drain, gate, source, body, library, link name, W and L. So the drain of P1 at node number 3, gate at node number 1, source is 2, source is connected up to node number 2, and body. Yeah, so one thing which I did not draw is this thing, that the body terminal is to be connected like this here. So this is body. Similarly, here also there is a body terminal, it is connected here. So let us also denote that this is the body terminal, right? Now it is easy. So drain, gate, source, body. So body of P1 is also connected to 2, and our library link name is P underscore MOS. Let us assume that we are using equal sized MOSFET. So we have for 120 nanometer technology, let us say that the technology is 120 nanometers. So we have W equal to 120 nm and L equal to 120 nm. Or if you want to have size equal to 5 like in microwind, then you can say that it is equal to 600 nanometers. Okay, so W equal to 600 N, L equal to 120 N. Similarly, we can define N1 NMOS. So drain at 3, gate at 1, and source and body are connected to ground. GND, GND, library link name, and we have again W equal to 600 nano, L equal to 120 nano. So we have defined the active components. Now we will define the sources. So the first source is Vin. Okay, it is connected between 1 and ground, and it is pulse type. So PULSE. So initial value 0, final value 5, delay is 0, rise time is 0.1 nano, fall time is 0.1 nano, the T on is 0.5 nanoseconds, and the time period is 1 nanosecond. So we have defined it. Similarly, we will define the second bias source VDD. So VDD is connected between 2 and ground, 2 and ground, and we can say let VDD be equal to 5 volts. So we will say it is connected between 2 and ground and the value is 5. So we have defined the sources also. Now we will link the libraries to our devices. So the directive dot model. So we have dot model space library link name. So library link name for PMOS is P underscore MOS. The library name is PMOS, and we will say I want to perform basic simulation. So level equal to 1. Similarly for NMOS, dot model library link name N underscore MOS, library name NMOS, again level equal to 1. Now we are going to define what kind of analysis I want to do. So I will say dot tran. So I will say dot transient, and I will say I want the step size to be 0.01 nanoseconds, and I want it to go for 5 cycles, so it is 5 nano. Now we have to print the output. So the dot print statement, we will say dot print, and we will say tran and output, that is voltage at node 3 versus voltage at node 1, and then we can say dot end. Okay, now we are going to highlight everything which is predefined in the language. So we are here, predefined W L N N. So all these are predefined. Whatever is in black is user defined, and whatever is highlighted in yellow is predefined. Similarly, the alphabet V is predefined here and here. This is predefined. This is predefined. N predefined. Ground is predefined. Similarly, dot model is predefined. Sorry, this is not predefined. This is predefined. Level is predefined. So level equal to NMOS level equal to. Similarly, dot tran is defined. N is also defined. Dot print predefined. Tran is predefined. V and V are predefined. Dot end is predefined. Okay, like that. Clear? Yeah. So in the syllabus we have DC analysis, we have AC analysis, and we have transient analysis. So AC analysis I'll teach you some other time. Let us study how we can perform noise analysis in any given circuit. So suppose if I want to find out that what is the noise at the output node with respect to the input node. So this is how it is. So noise analysis in SPICE. So for performing noise analysis, we have a predefined syntax in the language. It is like this: dot noise. It's a directive, dot noise. So understand that when I say noise analysis, the SPICE model will calculate a cumulative effect of three kinds of noises: Johnson's noise, short noise, and flicker noise. That is what the literature says. Dot noise, then we have V for voltage, voltage between node 1 and node 2. Then we have SRC. SRC means, always understand one thing, that the noise is always reference to voltage. So we have SRC. Then we have to tell, now we know noise analysis means what? It's a plot of noise in dBs versus the frequency. So basically it is like a frequency response. So we have to tell to the SPICE engine that the x-axis or the frequency axis, does it have to be linear? It has to be decade or octave. You know that octave means 2 times, decade means 10 times, and linear means linear. So if I have a frequency of 1 kilohertz, then the first octave of 1 kilohertz is 2 kilohertz. The second octave of 1 kilohertz is 4 kilohertz. On the other hand, if I have the fundamental frequency as 1 kilohertz, and if I say what is the decade, the first decade of 1 kilohertz is 10 kilohertz. The next decade is 100 kilohertz. The third decade is 1 megahertz. Getting me? So we should understand what is linear, what is decade, and what is octave. So we can tell to the tool, we can tell to the engine that whether I want to have a as OCT, that is octave, decade, or you want linear. Then we have number of steps, step size. Then we have f start, and we can have f stop, right? And we have f stop. Okay, so it's very simple. So now we want to perform the noise analysis at this point. This point we want to perform the analysis. Okay, so we want to perform analysis at this point with respect to this point. Okay, this point. Okay, so output voltage, noise in output voltage reference to the input voltage. Okay, so how do we write this? We will say dot noise V, I will say output node comma ground. Actually we never say fine. So it's 3 space ground, and we have source, we have V1. So it is basically V bracket source. So here this is a node number. Here is a node number. Of reference. So noise is always reference to something. So we have V parenthesis 3 space ground V bracket 1. And if you want to perform a decade analysis, that is like on a semi-log paper, we can say DEC. We can say I want 1000 steps. I can say start frequency. If I know that a particular noise is existing from 1 kilohertz, I can say 1K, and you can stop at 10 meg. Don't write capital M. Okay, don't write capital M. So you can understand here in SPICE, So I don't think so I'll be able to finish crosstalk today. So I will just make a list of topics which I'm going to give in the notes form, handwritten notes form. Is that okay? So these are the four topics which are from this unit, which I feel that handwritten notes can be given. Okay. I will not be taking them in the class because there are other important topics to be taken. Okay. Yeah, theoretical. Fine, there are 3 more minutes. If you want, you can start filling the feedback, or else you can fill by the end of the day.